Ask them looking at evidence which things they're doing wrong, and then they could improve on this. It's like super chaotic.
But they have like, I don't know, like 5 meetings and 4 were like from that's dragging them. They're really
one of the student innovations.
oh,
so two of my friends leave there, so then we go radius around and have to leave from like 10 a.m. to like 5 p.m. or something.
What happens in the sometimes leftovers.
The guy that I met, so they always were like bomb mates, like in a really cool way. But now it's really like exploded.
no. Well, I was in Mexico a month ago and they have an app for my friends. Like if you go camping, not a lot.
Still have not super far. I thought it was there in around 2000s. I think I got to one. And super careful, and he has some stories there. Clients or entering people,
Yeah.
So everything major part of the countries there are on the some parts are. Hear the other minds step from that.
Yeah, makes sense.
Oh, why?
Something wrong with it. To look for you.
One of my friends is leaving next week, so I need to plan like 2 days or something. These things think of everything, but don't think about it.
How was your weekend?
I'm just drinking beer.
Oh,
Now we're really nice place called Iceberg. We go like in German, coffee.
yeah. Like typical.
Okay, sorry for interrupting. Okay, good. So let's continue. So we have seen the relativistic species. Let's give a look at the non-relativistic one. And these guys are going to be interesting as well. Okay? So non-relativistic components. So we are going to consider massive particles because these are the ones that we are interested in this moment. And in a non-relativistic limit, kT is much smaller than mc squared, where m is the mass of your particles. Okay, so we're considering matter here. Okay, matter that we have seen as a pressure that is negligible here, kT over m rho. This guy is negligible, and it's going to be pressureless. Okay, this we have seen before. And with that, we call it dust. Okay, this is just jargon. It's not the one that we find on the floor, but also dark matter is considered as dust. Actually, dark matter is a very good dust. Then we have to split these non-relativistic components in 2 different parts. Okay, one are going to be the baryons. that we are all familiar with. Me, you, and this sort of particles, okay? That's the matter that we know very well. They interact through electromagnetism. That's why we can see them. I can see you, you can see the board, and so on and so forth. That's why they create molecules and cells and us in the end, okay? So extremely complex particles that even give rise to life, okay? So very exciting. It's since we are born that we know their existence. But there is a problem with structure formation, because there are not enough. There are not enough baryons to explain the dynamics of the universe as a whole, and again, they are even not sufficient to explain structure formation. We need more matter than what we actually are. That's why we introduced dark matter, okay? But let's stick to the baryons for the moment. And why I can say that there are too few? Where are we getting? How can we say that? Okay, well, because we have observational constraints. For example, coming from the Big Bang nucleosynthesis. Okay, so Big Bang nucleosynthesis, and we have constraints. Remember, we have a universe which is composed by proton, neutrons, the electrons and so on, but it doesn't matter. These are the species that we are interested in now, so protons and neutrons. And the temperature of the universe is going down, and the energy is low enough to allow them to bind together. When they bind, we know that so protons is basically hydrogen, okay, it's fully ionized hydrogen. We start to have protons and neutrons that are starting to stick together, forming deuterium, which is just an isotope of the hydrogen. Okay, it's not just P2 alone, but there is also a neutron inside. And once we have the formation of deuterium, we can have other protons sticking together to form helium through the chains that we have seen during the cosmology lectures. And not only that, there is a little bit of lithium and beryllium that are formed as well. Okay, so that's the formation of heavier nuclei in our universe. And this is happening through a chain of nuclear fusion, in which there is the interplay of all these different species. And you know that the deuterium is extremely important because you cannot jump, or let's say it's possible, but it's extremely unlikely that you can go through 4 proton, neutron, etc., to stick, for example, together in helium-3 or helium-4, okay? Because it's because basically the only species that, the only reaction that sort of makes sense is just 2-body interactions, okay? You can have 2 particles that meet together, but 4 with the right combination that meet at the same time in the same place, it's very unlikely. So that's why the deuterium is extremely relevant for the process. Good. So, okay, this is happening. How can we get a constraint? Well, because we know a constraint on the number on the amount of baryons that we have in our universe. Well, that's because we know that neutrons are decaying. So we have beta decay, and the number of neutrons is going down as a function of time. So our poor neutron is decaying, so it's basically going to be broken into particles, so a proton and an electron, still neutral, and an electronic neutrino, antineutrino, sorry. Okay? So we have beta decay. Therefore, the number of neutrons is going down, not because the expansion is increasing, but because they are disappearing. Okay, they are dissolving into these other particles. The number is going down despite the expansion of on itself. Now, what happens instead if the number of baryons is larger, okay? Let's assume that we have a larger number. The larger is the number of baryons, the faster are the reactions. Faster. So let's write it like this. So the larger is the density of baryons. The faster, let's write faster, faster are the reactions. Because you know the reaction rate of a particle is related directly proportional to the velocity of the particles, but in this case is relevant the dependency with respect to the density. Okay? And then we have the cross section. Okay? So this is extremely relevant. Larger density, faster reactions. What does it mean? That if B is, for example, larger, the reaction rate is the reactions time in which this phenomenon is occurring is going to be compressed in time. Because this starts, the energy goes down, they start to stick together, so the process is starting, but at a certain point it stops. When all the neutrons are basically swollen into the helium. Okay? And the reaction cannot be still some around, but the probability to continue with the reaction is very low. So we have a halt in this reaction, so there is a time frame. Larger rho means that this time frame is smaller, right? For the time, let's take the time in which this is happening. Here we have the start, here we have the end. Start and end get compressed. What's happening? Why is then this relevant? Well, because the neutrons don't decay about what happens. I'm a neutron, I'm decaying, okay? And I'm decaying always with the same rate. It doesn't matter, there is no dependency on rho B. Therefore, if from here to here I have a certain number of neutrons that decay, if this gets smaller, the number of neutrons that decay is going to be smaller. What's happening? What does it mean? That if rho B is larger, then the number of density that I would have is actually smaller, because less of them had the time to decay. Therefore, you have a change in the ratio between the neutrons that you have and the total amount of baryons. Okay? Is it clear? Okay? So, start of the reaction, end of the reaction depends on the reaction rate that is proportional to the density. More density, less time. Less time means that less neutrons can decay. And therefore we have more neutrons. And if we have more neutrons, we can produce more helium. And we can produce more deuterium. Okay? Therefore, by measuring the amount of deuterium and the helium, and hydrogen, sorry, which is left out in the universe, we can have a constraint on the amount of baryons that is allowed. Okay? This is done through observations of quasars. That's an example, okay? So what happens is that you are here, and you are observing the universe with your spectrograph. You might have a quasar, which is very far away. We are talking about Z much larger than 1, and with much larger than 1, I mean 7, 5, 7, 1, 5, 7, that's the order of magnitude. And along the way, you see, you have the matter which is distributed along the side. You have your spectra, you can distinguish the elements one from each other, because you see lines that can be in absorption or in emission. Okay, typically in absorption in this case. And with these measurements, you can get a ratio between deuterium and hydrogen. So you see how much of these guys that are formed are left, and this depends on the number of neutrons that are still available for the reaction to take place, is equal to 3.0 plus minus 0.4, 10 to the minus 5. And this gives you an omega for the baryons n times 0 of 0.020 plus minus 0.002 h to the minus of 2. And this is at 2 sigma. Okay, typically, if this is not mentioned, astronomers, cosmologists give measures at 1 sigma. Okay, it's not like particle physics that give like at least 5 sigma. Okay, this is already very generous. Okay, so you see that's the value you get, 0.02% times h to the power of minus 2. And if we assume h to be 0.7, then we get that 4% of our universe can be constituted by baryons. 4% if h 0.7. That's little. That's too little to even explain structure formation. Okay? Then that's not the only constraint that we can possibly have. So that's these are the quasars. But we have also CMB observations. Because the pressures, the baryons on small case do have a pressure. That's relevant. That's relevant. And if they have a pressure, their presence affects the sound speeds of the medium. It's affected. And actually, the sound speed goes down. So CS goes down if rho B is larger, then CS gets smaller. So you remember that our fluiding, the equations describing our fluid is an oscillator, is a damped oscillator, okay? And the oscillations get larger if the sound speed is smaller, because the sound speed enters in these oscillations like the spring constant, okay? Therefore, the oscillations can get larger. It makes sense. There is more pressure. No? There is the pressure given by the baryons. So the oscillation can get larger. And if we measure the cosmic microwave background spectrum, so we have our K mode, actually, our harmonic mode C that we have seen in cosmology. And we have the temperature fluctuations of measurement from our power spectrum. You know that we get something like that with our exponential cutoff down here, and this guy will get larger. You get rho B, which is smaller, then CS is larger, and on the opposite, this guy is going to become smaller. The amplitude of the oscillation drops. And drops, gets smaller. Okay? Therefore, by just measuring the amplitude of the first peaks, one can get a value for the amount of baryons. Rho B, now with respect to the normalized with respect to the critical density at nowadays, from W map observation, one gets 0.02267 plus 0.00058 minus 0.0059 h to the minus of. That's W map. And I suggest you to look into Planck, where the value has been updated, but we are talking about these numbers. Okay? And you can look at the agreement between the two observations. That's very good. Okay? We get coincidence between these two observations. Therefore, by looking at this number, so we have 4 of baryons, and they are not enough to explain structure formation. They are not enough to explain the behaviors of the CMB, the features of the CMB. Okay, because we need an additional amount of matter with which its own gravity helps the collapse to take place. No pressure, pressureless matter that helps the collapse. Okay? Need dark matter. That's the only way to solve the problem, but the one which is kind of in fashion, if you wish, or that I also would suggest, is going to the direction of looking dark matter particles. Okay? Particles which are pressureless. So W of dm equal to 0. We need something that contributes to the overall dynamics of the universe and to structure formation as a pressureless matter distribution, okay? Which cannot be baryons for the reasons I mentioned because of measurements. Okay? Good. Now let's give a look at dark matter. So we had the non-relativistic particles. We look into baryons, and now we see that we need dark matter. Dark matter that, as we said, must have an equation of state equal to 0, because otherwise, if this guy would be equal to 0, would affect in a different way the amplitude of the cosmic microwave background peaks, would affect structure formation in a way that we don't see. Okay, so observationally, we need a contribution of matter of this sort. And by measurement of cosmic structure formation, cosmic structure formation, which means clustering of galaxies, for example. Might be cosmic microwave background, in which we're looking at overdensities that are forming, that are present in the distribution of our medium. We are looking at galaxy clusters. A number of galaxy clusters, for example. Then what we get? We get an omega, dark matter. Now I give you again an example based on the cosmic microwave background for consistency with the previous results. 0.1131 plus minus 0.00034 h to the power of minus 2, and this was from WMAP. Again, I have to put here the numbers of Planck. I will, but look here into Planck as well. But the story doesn't change much. We are talking about 25%. Okay, again, if we set h equal to 0.7, we are talking about 27% of the amount of matter. Okay, that's nice. We can assume we need this sort of stuff, so we can start with dark matter particles. What are they? So which particles of which kind of matter? Well, they could be some new fundamental particles. That escaped the production in our accelerators. We are producing particles in acceleration, in our accelerators. They are not popping up. We don't see them. At the energy levels that we are at the moment, we don't see dark matter particles. Okay? We could detect them. We have detectors, right? They have a very low, they don't interact with gravitational waves, they're not interacting with electromagnetic waves, but perhaps there is some other interaction through some other force with other elements. Maybe the cross-section is tiny, small, because whenever we talk about pressureless particle, maybe the pressure is not identically zero, it's nearly zero, okay? Which would mean that the cross-section of the interaction with the other species is very, very small, okay? Maybe not zero. So people are also trying to detect them with detectors. We have detectors, CSM, for example, which is mounted on the space station, on the International Space Station. They are trying to detect, to see, to have a direct detection of dark matter particles. And there are also other experiments on the ground that are trying to do that, especially in labs that are placed underground. Okay, for example, in Gran Sasso, there are experiments that are trying to detect dark matter. Why underground? Well, because what you're trying to do is to, your lab is here. It's nice to have like a cave, like a Batman. It's very cool. But the point of being in a cave is that over your head there is a huge amount of matter. Okay, the mountain, the Gran Sasso mountain, and therefore the other particles can perhaps penetrate into the ground and boom, they interact. They don't reach your detector, but dark matter has a very small cross-section, if they exist. They have a very small cross-section, and basically they can detect, go through your detector, and then continues, or you can hit them. But you have basically a shield from the other particles, and this reduces the background of your measurements. Okay, so also this one is another way to try to detect dark matter particles in a direct way, not indirectly through cosmological observations. Okay, because through cosmology we have an indirect evidence for the presence of dark matter. Right? We see structures that are forming, but this doesn't mean that we detect a particle. Okay, we can characterize it. We can set limits on the cross sections, on the mass, blah blah blah, all of that. But it's not a direct interaction. So cosmology, at the moment, is the only one that delivered the results. All these other experiments, at the moment, they are still giving upper bounds on the cross sections. Upper bound because we don't see anything. We arrive at this limit, and the cross section must be smaller than that. Okay. So we have new particles. For example, there are the WIMPs, weakly interactive particles. Is one of the candidates for dark matter, and there are a forest of different ones. What about neutrinos? Well, neutrinos are neutral. They are not participating to electromagnetic waves interactions, right? Therefore, we don't see them, they don't absorb, they don't emit. They could be then. That's a dark matter, okay? What's the problem? That W is 1/3. And they do have an effect on cosmic structure formation. And therefore, if their number is too large, as we have seen, then this would have an impact on cosmic structure formation. Therefore, they cannot be neutrinos. What about black holes? Black holes, think about it, these are just, they could be baryons. We don't need to invoke a new particle out there, okay? They could be of baryonic natures, coming from some mechanism, and we might have black holes that are floating around. We don't see them. They are not nor emitting nor absorbing radiations. They are a metal component with zero pressure. They are small, therefore they are not hitting direct interactions. We don't give you a pressure term. Okay? Why not? Well, they cannot be large. Not too massive. Why? Because astrophysicists search for them. Okay? There were campaigns, and they were looking for the so-called machos, which are associated to massive black holes. Okay? How did the people do that? Well, they took their telescope, they were observing the galaxies, stars within our galaxy. You have your star, and imagine now that you have a black hole that is passing next to a star, right in front of you, okay? You are the observer, I am the star, and the black hole is passing almost in front of you. What's happening? Massive object, general relativity tells you that the trajectory of photons are bending. They are following geodesics. The geodesic is not straight, and you get a distortion. You have a gravitational lensing taking place. And the black holes are going to act as lenses. They are acting as a lens. And what you observe is the magnitude of your star, so that's let's say that's the flux that is coming from your star as a function of time, and you observe it, you observe it, you observe it, you observe it, you observe it. Maybe there is an intrinsic variation. We know that stars also have intrinsic variation of the luminosity curve, so we can even imagine that our light curve is, for example, a Cepheid or something else in which the luminosity is changing as a function of time, but at a certain point, peep, we have an enhancement in the luminosity that has a very specific shape due to gravitational lensing. Okay? Did people observe objects of that sort? No. Okay? They can use it to detect moons around planets, extrasolar planets. Okay? So the sensitivity is extremely high, but no machos have been found. Okay? No machos. Can we rule them? Well, actually I should do here. And therefore they should be, they cannot be massive, but they have to be of baryonic components, but they cannot be baryonic because, again, we go for in the trap that there are not enough to form them. And therefore, they can be baryonic, but they might have been formed at very, very, very early times. In this case, we're not talking about machos or black holes that are of astrophysical origins, but we are talking about primordial black holes. Okay, that's an alternative. Not astrophysics, they formed before, right after inflation. They got formed by some mechanism because of basically, you can have you have the inflation basically bring to macroscopic scale the density fluctuations, right? Under certain circumstances, you might have the collapse of those overdensities, forming primordial black holes. Okay, they could be dark matter. Okay, it's not very popular. Okay, as a way of solving the problems, that's not very popular. So these are three ways. This one is the one that we are going to follow, but could be another one. There could be a fourth way that actually we are using the wrong model. Lambda CDM model is not the right one. Because, for example, the universe is not homogeneous. We might be living in a underdensity. Okay, so imagine that we are living here. The universe has a density that is changing, the spatial distribution of density of the universe is not homogeneous. And imagine, for example, that here the density is larger with respect to that. It's expanding, all of that, whatever. But what is this amount of density doing on the surrounding matter? Okay? For example, galaxies. We measure a galaxy here is going to be accelerated in this direction. Right? What do we measure? An accelerated expansion, which is not due to the overall dynamics, but is due to the fact that we have an overdensity there. Okay? For example, Bondi models explain the acceleration of the universe in this way. Is it popular? Not much, because if you use this sort of models, for example, and if you place yourself here, you would see an inhomogeneities in the expansion. Therefore, by looking, for example, at the redshift supernovae in different directions, you realize the fact that you must sit in the middle of such a underdense region. Okay? Doesn't sound good. Okay? Doesn't sound very healthy. Good. So these are the particles that we are considering. So we have our photons, we have our neutrinos, we have the baryons, and we have dark matter. Now we are going to always to consider a cosmology which is populated by this sort of elementary particles. Okay? At the beginning, I introduced another sort of matter, which are scalar fields. Scalar field that we need to invoke to solve our issues with the cosmological constant. So if we set our cosmological constant equal to 0, then we need a scalar field to explain the accelerated expansion. So these are the three ingredients that we are going to consider during these lectures. Okay? Now I give you, we conclude with the motivation of why we are not satisfied with lambda, but we are going to go in this direction so that we know, I mean, so that we are sure that we are doing, you know, that all the derivations that we are going to do have a meaning, why we do that, so this is going to be the motivation for all of that. And to arrive at setting lambda equal to 0, we need to have a reason to do that. Okay, why? Lovelock's theorem tells us that this is a term perfectly valuable in GR, in general relativity, right? So we have our R mu nu minus 1/2 R G mu nu plus the cosmological constant G mu nu plus equal to the some constant, and then we have our energy momentum tensor T mu nu. Okay? That's the most general theory of gravity based on geometry, which satisfies energy conservation in 4 dimensions with derivatives of the metric up to 4th order. Okay? Lovelock's theorem. Mu nu equal to 0, derivatives of G mu nu up to, not off, up to 2nd order, which is based on geometric gravity, geometric theory, geometric gravity, such as GR, and in 4 dimensions, as the space-time that we are describing. This is the most general theory you can build up. There is not another one. Okay? So for lambda, yeah, why not? It's there, might be there, but what we try to get to understand this guy is by bringing it on the other term and define it as a fluid, okay, as an effective fluid. Therefore, if we bring the cosmological constant on this side, we will get the Einstein field equations up to here. And we can call this guy, let's put a minus here, let's put a plus here, and this guy is going to be our energy momentum tensor for lambda. Okay? Then what we can do is to impose this guy to have the form of a fluid T mu nu of our cosmological constant is c to the power of 4 lambda 8 pi g, where these constants are coming from this alpha here. Yes, alpha goes here, from this alpha here, okay? And we impose it to be a fluid, rho plus p over c to the power of 2, u mu plus p g mu. We are imposing that, okay? What if this guy is a fluid? Well, do you see any dependencies with respect to the observer? No. Therefore, this term here must be equal to 0. No matter on the observer frame, this guy must be equal to 0. And therefore, we get the equation of state, because rho plus p over c squared must be equal to 0. What does it mean? That rho, that the pressure of lambda, I isolated this term, is equal to minus rho c squared. What is minus? That's the equation of state parameters of lambda. Minus 1. That's where the effective equation of state parameters of lambda is coming about by imposing this stuff here. Okay? And look what's weird. What was the one of photons? 1/3. That's positive. That's negative. Huh? More density, less pressure. Negative pressure. What does it mean? That's the contribution, this minus term, that gives you an accelerated expansion. And this, you get the acceleration expansion because W's lambda is smaller than minus 1/3. That's the condition for acceleration. Okay, lambda works. Lambda works. What is the problem? Is here. There is no dependency on u mu u nu, which is a typical characteristics of vacuum. Vacuum energy. If you want to go on a fundamental level, not an effective theory as GR, but you want to associate it to something related to particles, that's what you get. Okay? Vacuum energy. And this is a problem. One of the problems. This is one of the problems for particle physics. Okay? So, I'm going to show you why this is a problem for particle physics. So we are going to give a look a little bit into that. Not much more with respect to what we did in the standard cosmological lecture. So we're going to be still part of the recap. Because there is a very strong inconsistency between the values that we observe by looking at the universe for lambda and what is produced by a particle physics approach. Okay? Plus, as I mentioned earlier, the cosmological constant cannot explain why today we have this value of the cosmological constant very similar to the one of matter. Okay? It cannot be explained. Okay? We have these two problems: coincidence and the smallestness, or you say how small is the cosmological constant. Okay? These are the two problems that we have. Good. Then we can stop here. Well, actually, there is another thing that you can explain, used to explain why there is this coincidence problem, which is of anthropic origin. We exist. Okay? We exist, and we exist because this is the universe with the possible largest values of lambda, for which the universe had the time to give the formation of cosmic structures in which we formed. Okay? Somebody said, oh, it's a philosophical problem, this one, because, why are we so special? No, we are just baryons that had the physics that we have, and we just formed. So as the nuclei formed during baryonic nucleosynthesis, we are just another phenomenon of baryons that is occurring now. we are observing these baryons organized as we see them, and this is the smallest value that we can possibly have to let the universe have the time to form ourselves. Okay? So it's philosophical, but maybe not really. Okay? Anyway, so this would be another way to explain the coincidence problem of omega lambda and omega m, very similar nowadays. Okay, good. So next time, now that we know the three ingredients that we are talking about, baryons, dark matter, scalar fields, neutrinos, we know how to associate, to describe the cosmological constant in terms of a fluid, for which we derived an equation of states that, yes, satisfies the accelerated expansion of the universe. And in the next lecture, I'm going to show you why it's a problem to associate it to, going to a more fundamental level on particle physics, why giving it the values of the cosmology, associating it to the vacuum energy is a problem. Okay? Why lambda is not exactly zero, and the problem of the coincidence that is still there also for dark energy. Okay, but we will see that later. Okay, good. So thank you very much. We are done for today. So, yep.
So here, temperature equal to, it's proportional to photon's temperature.
The photon temperature, yes.
Is it valid nowadays? Because isn't neutrino like they have cooled enough such that they are not relativistic anymore?
No, they're still relativistic.
Oh.
But the point is that they're not anymore in contact with the photons. Therefore, the two temperatures are completely detached from this epoch on.
So even like nowadays, neutrinos are still relativistic.
The cosmic background, yes. Not the one, the one cosmic from the sun, for example. They are not the neutrinos I'm talking about. These are the neutrinos that are formed by the sun, within the sun, the nuclear reactions that are occurring within the sun. That's a different family, okay? I'm talking about neutrinos that are formed at the background.
Like 1 point something Kelvin. Right.
Yeah, but they have very small mass.
Okay.
That's a matter also of the mass. That's why also their mass should be very small. Because if their mass would be larger, they would not be free, so they would become non-relativistic quite early, and they would not give you this damping effect on the fluctuations of on the power spectrum. For it, there is a mass limit on the neutrinos, which is coming from astrophysics and cosmology.
One small question. Now, at the end, what did we say that rho plus p over c squared was 0 for the lambda t lambda? We assumed it was a fluid.
Yes.
We put p plus rho over c squared, and we said it was 0. And from there we got that w for lambda was minus 1.
Yes.
Why did we say that?
Because there's no dependency on u mu, u nu. So if you look at this expression, there is not dependency on mu, u nu.
Oh,
okay. Okay, so this is just a constant. You have the metric. So all of this term, no matter what is the velocity of the observer, must be equal to 0, and leads you to that.
Because of different systems, and you would not have a seemingly a constant then.
Yeah.
Okay.
Yeah, got it.
Okay.
Thanks.
I,
I have another question.
yep.
So we said that the omega m are like fine tuned. They're so close to each other, and why do they have to be so
Yes.
close? And so we create another dynamical dark energy so that they're always close all the time.
So that's the thing. So here we have something that is responsible for the expansion of the accelerated expansion of the universe. If we measure it, we get this value. The same for baryons. If we measure it, that's the baryon. They're very close one to each other. So the problem is, why are they so close? That looks like a coincidence. They're not related in nature. Why should be they close to each other?
And you said that we wanted to make them close to each other all the time from.
No, is one of the ways to do it. So if you have the cosmological constant, is one number and is not changing. Okay, so this number has been set by for some, you cannot. Is a fixed number and it has to be perfectly coincidence with this omega lambda that we are measuring now. If you instead you're setting, okay, there is no cosmological constant contribution because of the energy the vacuum of the energy, the vacuum energy is zero, okay, for some mechanism. Then you must invoke dark energy. You invoke dark energy, and this gives you more freedom because it's a function, it's not one number. And this function is reacting to the dynamic of the universe and all of that. Okay? Therefore, through some mechanism, you might have that, you might start with some random number, but then its dynamic brings it closer to the one of, naturally brings it closer to the one of matter. Okay?
Okay, but my problem is through observation, doesn't the lambda being constant agree with our observation of how universe expands and how structure forms?
It does, yes.
So
why change it? You say,
yeah.
because it does, but it's difficult to explain. It has these implications, these difficulties in say why the coincidence principle, why the fine tuning is so small. It looks very, very specific, very fine tuned.
But
okay.
Then if we change it, doesn't we change also possible like history?
We change it, but it has to be very close to the behavior of lambda. Okay, so you have if dark energy exists, then its behavior cannot lead you to a dynamics which is too far from the one of lambda. And there are mechanisms for dark energy that kind of naturally brings you there. Okay, so you basically pick up a fluid, which potential that characterize the behavior of the fluid, kind of starting from arbitrary or nearly arbitrary initial conditions, brings you to a fluid that behaves like lambda. It's very close to lambda.
Even though if the initial condition is very different from the constant we have now.
Yes, exactly. That's the point. You start from, doesn't matter where, but you arrive at what we see now. Okay.
Thank you.
But we are going to see that in details later. I have to stop there.